Welcome to this explainer. If you've been watching AI get smarter lately, you might not realize that the hardware powering it is undergoing an absolutely massive turning point. It's actually no longer just about building a faster calculator. The rules of the game, they have entirely changed. And to truly understand where artificial intelligence is heading, we have to look under the hood at the physical architecture that makes it all possible.
Which brings us to the biggest question we're answering today. Why did Google just literally split its AI brain in half? With their newest 8th generation Tensor Processing Unit, the TPU V8, Google didn't just release one chip. No, they released two entirely different chips. One explicitly designed for training AI and another explicitly built for running it. So, why the sudden split?
To figure that out, here's our roadmap for today. 1. The shift from flops to fabric. 2. The Great Silicon Divergence. 3. Topologies of destiny. And finally, 4. The AI infrastructure war. Let's dive right in.
Starting with Section 1, the shift from flops to fabric and the brand new AI bottleneck. So look at how the actual workflow of AI is shifting. We're moving away from those basic stateless generative AI chatbots, where you ask a question, you get an answer, and the bot completely forgets you even exist. Now we're stepping into the era of agentic workflows. In an agentic enterprise, AI agents are operating continuously. They're making multi-step decisions, simulating future scenarios, using tools entirely autonomously. And because of this, the bottleneck is no longer just pure math or flops, floating point operations per second. Instead, the new architectural tax holding things back is latency and memory retention.
And that is exactly where the KV cache comes into play. Think of this as the agent's short-term memory. When you have an agent call center handling a really complex multi-step customer service request, that AI needs instant sequential reasoning. If the chip has to constantly reach out to external memory just to remember what it was doing 3 steps ago, the whole system absolutely grinds to a halt. Memory retention is without a doubt the new critical bottleneck.
Moving on to Section 2, the Great Silicon Divergence, where we see the abandonment of the do-it-all chip.
See, trying to use a single do-it-all chip, that's become a huge economic compromise. Looking at the two pipelines, Phase 1, pre-training the AI, is the heavy lifter. It requires massive data bandwidth and raw matrix math density to ingest billions of tokens all at once. But Phase 2, agentic serving, which is actually using the AI to think and act, is the fast thinker. It requires ultra-low latency and massive on-chip memory to hold on to that KV cache we just talked about. They have fundamentally opposed bottlenecks.
When we stack them side by side, you can clearly see how Google natively split the silicon. The TPU-8's core mission is massive pre-training. It packs 12.6 petaflops using native FP4 precision, leaning really heavily on high-bandwidth memory. But look at the 8i. Its mission is low-latency serving. While its raw petaflops are slightly lower, its memory strategy is a total game-changer. A massive 384 megabytes of on-chip SRAM to keep data right next to the compute core.
Let's zoom in on the TPU-8 for a second. You can really think of this thing as an intelligence forge. Its sole purpose is to continuously bake massive intelligence without interruption. Google connects up to 9,600 of these chips together in a single superpod to deliver a staggering 121 exaflops of compute power. To put that into perspective, this is the massive brute force factory floor required to bake colossal world models like DeepMind's Genie 3.
But hey, pure brute force isn't enough, right? You absolutely need efficiency. Large language models constantly have to find specific data vectors in a vast sea of data. These are called embedding lookups, and they are highly irregular. They usually just choke standard matrix multipliers. That is where the sparse core comes in. It acts like a highly specialized routing librarian. It uses only 5% of the chip's area, but it accelerates these exact embedding workloads by a massive 5 to 7 times. So your main compute cores are never just sitting around waiting for data.
Now, for actually running those autonomous agents, we switch over to the TPU-8i, the agentic silicon. Remember that short-term KV cache memory? Well, the 8i features a 3-by-generational increase in on-chip SRAM, hosting 384 megabytes directly on the silicon. By keeping the agent's memory of past context right next to the compute, it completely bypasses the painfully slow process of fetching data from external memory blocks. It's brilliant.
And to make absolutely sure everything runs at maximum speed, the 8i introduces something called the Collectives Acceleration Engine, or CAE. Imagine a bunch of chips working together on a really complex chain of thought problem. They have to constantly share intermediate results with each other.
The CAE acts as a dedicated superhighway for this inter-chip communication, reducing the latency of those synchronizations by 5 times. It ensures the matrix compute cores aren't waiting idly for data, achieving essentially zero-wait synchronization.
All right, Section 3, Topologies of Destiny. It's time to rewire the network.
Because the actual physical map of these network connections, it literally changes everything. The traditional 3D torus layout is absolutely perfect for the heavy, predictable bandwidth of training across a massive superpod. But as we transition to multi-step inference, look at the boardfly layout designed specifically for the TPU-8i. The way these chips physically talk to each other had to be fundamentally rewired from the ground up.
Let's break down the math real quick, because the difference here is actually crazy. In a 1024-chip 3D torus configuration, reaching the furthest chip takes a maximum of 16 network hops. For training, that's totally fine. But for agentic workflows, where any chip might need to instantly talk to any other chip to route a token, 16 hops creates a massive latency tax. The boardfly layout uses direct optical long-haul links to restrict that maximum distance to just 7 hops. That 56% reduction eradicates the compound latency that normally paralyzes agent workflows, meaning your AI tools respond to you instantly, zero lag.
And tying this whole thing together at a totally unimaginable scale, by the way, is the Virgo Megascale Fabric. This optical backbone can link up to 134,000 TPU 8T chips with 47 petabytes per second of non-blocking bandwidth. It achieves this using optical circuit switching. Instead of standard copper cables, the chips are actually connected by microscopic mirrors that physically redirect light paths in under 10 nanoseconds. If a chip fails, the mirrors instantly reroute the network around the hardware failure in real time. Literally zero manual rewiring required.
Which brings us to our final section, number 4, the AI infrastructure war, a true clash of philosophies.
What we are really witnessing right now is a showdown between two vastly different ways to build a data center. On one side, we have the AI factory model, prominently championed by industry giants like NVIDIA. This is a modular, top-down integration of specialized standalone components, GPUs, CPUs, advanced networking switches. It offers immense flexibility and broad ecosystem support. On the exact opposite side, we have Google's AI hypercomputer approach. This is total vertical integration. The custom silicon, the optical networks, the cooling, the software compiler layer, it's all unified as one single optimized entity. The ultimate goal here is to eliminate data movement bottlenecks completely.
And naturally, this divergence has sparked a massive debate across the tech industry. You've got NVIDIA's CEO Jensen Huang critiquing the TPU ecosystem as being closed and overly specialized, arguing that a broad, general-purpose ecosystem is superior for rapid innovation. Conversely, Google argues that in the era of massive agentic workloads, general-purpose hardware forces you into compromises. By controlling the entire vertical stack, right down to their specific JAX and XLA software compilers, they believe they can squeeze out maximum throughput and prevent the starving chef problem, which is where incredibly fast chips just sit there idle waiting for a slow data pipeline.
Now, the financial impact of Google's vertical integration here is profound. When you're running a massive AI cluster, honestly, even a tiny 3% drop in efficiency costs millions in wasted power and delayed research. Through their optical rerouting and highly aligned software stack, the TPU V8 ecosystem claims a 97% guaranteed goodput. This means that over 97% of incredibly expensive compute time is actually spent learning and processing rather than idling, troubleshooting, or recovering from node failures.
So, bringing this all together, we're really looking at the 3 pillars of AI infrastructure supremacy taking shape today. First, workload specialization, eradicating hardware compromises by splitting the silicon natively into the AIT for pre-training and AI for inference. Second, geometric connectivity, defeating the latency tax through hyper-optimized physical network topologies like boardfly and the Virgo fabric. And third, systemic resilience, guaranteeing operational efficiency through light-speed optical rerouting.
Which brings us to this defining realization about where we're heading. The victor of the agentic AI era will not be the one who simply buys the fastest individual piece of silicon, but the one who commands the most cohesive, end-to-end execution fabric. We are honestly no longer just comparing chips. We are comparing entire interconnected ecosystems where the data center itself is the single computer.
It's just a fascinating evolution, from pure math to true architectural mastery. As this AI war definitively shifts away from isolated chips and into the realm of massively integrated, globally scaled ecosystems, who do you think will command the ultimate execution fabric?
Thanks for joining me for this explainer. I hope this helped map out the insanely high-stakes future of AI hardware.